Hello! In today's lesson, we'll explore how to set up and connect an ultrasonic distance sensor using Tinkercad, and we'll examine how it works through a hands-on example. First, we begin by adding an Arduino model to our virtual workspace in Tinkercad. After making sure the Arduino has been added to the project, we continue by adding a breadboard. Next, we will add the ultrasonic distance sensor to our setup. From the list of available sensors, we select the HC-SR04 model, which is a commonly used ultrasonic distance sensor. We then place this sensor onto the breadboard to prepare for wiring. Let's move on to making the necessary connections. In order to make the connections clearer and more organized, I will move the Arduino to the lower part of the screen. I will also reposition the breadboard and the ultrasonic sensor together in that area. First of all, we need to supply 5 volts of power to the VCC pin of the sensor. So we connect the VCC pin of the Arduino to the positive rail of the breadboard, and we change the wire color to red to emphasize the power line. Then, from the breadboard's positive rail, we connect to the VCC pin of the distance sensor using another red wire. Now it's time to set up the GND connection, which stands for ground. We connect the ground pin of the Arduino to the negative rail of the breadboard and set the wire color to black to emphasize the ground line. Then, from that same negative rail, we connect to the ground pin of the ultrasonic sensor, again using a black wire. Now let's configure pin 9 of the Arduino as the output pin for the trigger signal. We do this by connecting pin 9 to the trigger pin of the ultrasonic sensor, and we assign the wire color as pink. Next, we connect pin 10 of the Arduino to the echo pin of the sensor, using a yellow-colored wire to make it easily distinguishable. When we zoom in and take a closer look, we can see that the 5 volts of power is routed to the breadboard first. From there, it is connected to the VCC pin of the distance sensor. Similarly, the ground pin is connected to the breadboard's ground rail, which is then routed to the ground pin of the sensor. After that, we connected the trigger pin of the ultrasonic sensor to digital pin 9 and the echo pin to digital pin 10 on the Arduino. Now let's move on to the code section. Keep in mind that this setup can also be built in the real world. You don't have to use Tinkercad if you're working with real electronic components. I'm using Tinkercad here because it makes it easier for you to clearly see and understand each step in detail. Let's start by declaring the variables. First, we declare a variable called TrigPin as an integer and assign it the value 9 because we connected the trigger to pin 9. Next, we declare another integer variable called EchoPin and assign it the value 10. Then, we declare a long data type variable named duration to store the pulse duration. We also declare another long variable named distance to store the calculated distance value. In the setup section, we begin by setting the trig pin as an output using the pinMode function. Then, we set the echo pin as an input, again using the pinMode function. After that, we activate serial communication so that we can monitor the sensor values through the serial monitor by using serial begin 9600. Now we move on to the loop block to write the code that will continuously run. First, we use the digital write function to set the trig pin low, clearing any previous signals that may have remained active. It's important to start with a low signal to ensure that the pin is reset properly. We then insert a short delay using delay microseconds too. We do this to make sure that any previous signal is cleared and the sensor is properly reset before we send a new trigger signal. Even though 2 microseconds is a very short time, it's enough to give a clean and reliable low signal to the sensor. Then we use digital write again to set the trigger pin high, which initiates the ultrasonic pulse. And we maintain the high signal for 10 microseconds. This brief high pulse triggers the ultrasonic sensor to emit a sound wave. This is very important because this sensor requires 10 microsecond high signal to start sending out an ultrasonic sound wave. If the high signal is too short or too long, the sensor might not respond correctly. So we follow the timing specified by the manufacturer to make sure it works reliably. After this, we set the trigger pin low again to end the signal and complete the transmission. Now that we've triggered the pulse and stopped it, it's time to measure how long it takes for the signal to bounce back. To do this, we use the pulse in function to measure the time it takes for the echo pin to receive the returning signal. This function records how long the pin remains high, which corresponds to the duration of the round trip of the ultrasonic pulse. So we write duration equals pulse in echo pin high. This line of code calculates the total time from when the sensor sends the signal to when it receives the echo back. Next, we calculate the distance using the formula distance equals duration divided by 2 and again divided by 29.154. We divide by 2 because the signal travels to the object and then back again, so we only want the one-way distance. We divide by 29.154 because that's the approximate speed of sound in microseconds per centimeter. As we mentioned in the previous lesson, using the formula in the comment line will also give you the same result, so if you prefer, you can use that version of the formula as well. Now we will print the results to the serial monitor so we can see the distance and duration. First, we use serial print signal moved to print a label. Then we print the duration value using serial print duration. We also include the unit of measurement for the duration using serial print line, microseconds. After that, we print the distance with a label using serial print distance. And we print the calculated distance value using serial print distance variable. Finally, we add the unit centimeter with serial print line cm to show the distance unit. To control how often the measurements are taken, we add a delay. For example, delay 1000 will take measurements every second. If we didn't add this delay, the loop would run very fast and the Arduino would constantly send data to the serial monitor, making it hard to read and cluttered. Also, constantly triggering the sensor too quickly might cause inaccurate or overlapping readings. At this point, we've written the complete code for this setup and now we can observe the distance readings. We scaled down the components to test the distance sensor's detection area more effectively, and we made the serial monitor visible to clearly observe the results. Let's run the simulation to see how everything works in action. We can now see the distance values updating based on the simulated object, and the same values appear on the serial monitor. If you can't see the detection range of the ultrasonic sensor, just one click on the sensor in Tinkercad will generate an object for it to detect. The distance between the object and the sensor is displayed above the sensor in both centimeters and inches. On the serial monitor, we can see the time it takes for the signal to travel in microseconds as received from the echo pin, as well as the calculated distance based on that duration. It currently shows a measured distance of 124 centimeters, and the duration is approximately 7,200 microseconds. Let's move the object closer to the sensor to see how it affects the readings. We see a value of 46 on the serial monitor, while the sensor itself shows 47.2. Even though Tinkercad simulates electronic components digitally, it still tries to imitate real-world behavior, including small inaccuracies. This kind of difference can also happen in a physical circuit, because a small margin of error is always inevitable in distance measurements. Now let's move the object away from the sensor and observe the results. When the distance between the object and the sensor is 291 centimeter, we observe a minor difference in the value shown on the serial monitor. We have completed both the theoretical and practical training related to the distance sensor. In our next lesson, we'll create an exciting new project. We'll add LEDs that change depending on the distance detected by the sensor. Thank you for watching, and I wish you all good luck with your projects.